Okay, so welcome back to part 2 of section 5.1. Last time we were talking about, well, we have a function, so for today the function we're going to start out with is x cubed, and we want to approximate the area over an interval, so like, for example, 1, 3. Graphically, we have something looking like this. Here's 1, here's 3. You want the area. What we're asking for is, what is the area in between? Okay, and we were doing this by taking rectangles and finding the area of those rectangles to approximate the area under the curve. Okay, so for this example, I want us to, just to get into it, start out with only 3 rectangles. Now, that means we want to split our width of our rectangles, that is the x value, to be 3 minus 1, taken from the interval, all over 3, or 2/3. So you can make these intervals, you have starting at 1 and you add 2/3, so that's going to be 5/3. Next interval 5/3, 7/3, and then next interval 7/3, 3. And then from here you ask the question, well, do we want to do a left sum or do we want to do a right sum? Okay, so a left sum, we'll call this L3. You have each rectangle has a width of, 2/3. And the height, if you're doing a left sum, will be f of whatever your left endpoint is. So f of 1 plus 2/3, f of 5/3, plus 2/3, f of 7/3. So that's going to be 2/3 plus 2/3 times 125 over 27 plus 2/3 times 343 over 27. And as a decimal, that will be 12.22 repeating. Okay, so you can do a similar thing with the right endpoints, and it will be a very similar process. But now, instead of choosing the left ones, you plug in the right endpoints, and that will give us R3. So 5/3, 7/3, and 3. And that, what will that give us? Well, you can do the calculations. This will be 29.55 repeating. Okay, so let's make this into a table. Right, because this is one approximation. We could try to increase the number of rectangles, and that will give us a better approximation. Right now we have 3, and if you look at ln, that was 12.22 repeating, and then you had rn, which was 29.55 repeating. So why don't you do number 4 and number 5? Okay, so I hope you did number 4 and number 5. Remember, the widths do change. Instead of 2/3, this would be 2/4 or 1/2, and also 2/5. So your intervals change. You have to compute this ln and rn. Sort of similar. For the number of rectangles tells you the number of terms. And when you do the computations, you'll get 14, 15.12, 27, and 25.52. That's just getting some practice with this. Okay, and then you can increase this. You could do, say, 10 and 100 to get better approximations, which I would not ask you to do that many on, say, an exam, but here are, if you actually sat down and did them, this is what you would get. Approximately, what you're getting here is that the ln, the left sums, you have them sort of increasing, and they're sort of getting close to 20, I would say, just looking at this by table. And the RNs, which was the overestimate, is decreasing also to about 20. So, what can we do with that information? Well, we know that this ln is an underestimate. You can do that by just looking at the graph itself. X cubed is an always increasing function except at 0 where it's not increasing. And so it's increasing on this interval. So whenever since it's increasing, if you take the left endpoint of the interval and make a rectangle, it will be an underestimate. Right? You have something that's increasing and you take the left endpoint, it will be an underestimate. Versus if you take the right endpoint, it will be an overestimate because you have this other little bit. So if I call the true area A, we have this thing happening. So I could take a limit of both sides, but they're looking like that this one goes to 20 and this one goes to 20. So by the squeeze theorem, I'm going to say that the true area is probably 20. And so that does help, and that does help, and now we have, okay, this is what the true area is. Even if we had to go through a lot of work to get there. 100 rectangles is a very tedious calculation to do. Okay, so I'm going to erase this chart. Okay, so for the next example though, so we had that function x cubed, and we're going to look on 0, 1 now. We could go through and do the table, but all we were doing is taking a limit, and we know we have our limit laws, and we have other things we could do, like now we have L'Hopital's rule to help with taking limits. And it looked like that if we took this limit as n goes to infinity of ln, or limit as n goes to infinity of Rn, we got what that area was. So why don't we just take ln, simplify it in some way, and then take the limit and see what that turns out to be. I will start out with the true area of this thing is going to be 0.25. Okay. So how did we make, if we're trying to do it in the most general case for ln, How did we get ln? Well, we had our width, and that was the length of the interval divided by n, or 1 over n, if we're doing it in the most general way. And using that, we made our intervals. You would start at 0, and then you would do 0 plus 1 over n, and then 1 over n to 1 over n plus 1 over n gives you 2 over n, etc., until you get to n minus 1 over n, and then n over n, or 1. Okay, so if we're doing ln and we want to come up with a general formula for it so we could take the limit, well, it's going to be our width, so that's 1 over n, times f of our left endpoints, plus 1 over n, f times our next endpoint. And this continues all the way until we get 1 over n f of the last endpoint, left endpoint, which is n minus 1 over n. Okay, I can factor 1 over n and plug in each of these x values to the function. This will be 0 cubed plus 1 over n cubed plus 2 cubed over n cubed, all the way to n minus 1 cubed over n cubed. I can take out the divided by n cubed because 0 divided by n cubed is still 0. This will be 0 cubed plus 1 cubed plus dot 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 plus n minus 1 cubed. Okay, so what can we do with that? Well, as it turns out, there's a particular rule that there is. If you have 1 cubed plus 2 cubed plus dot 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 plus some number k cubed, then this is just k squared, k plus 1 quantity squared over 4. So how does that apply here? Well, if we clear some space and write it for ln, we have 1 over n to the 4th, and the 0 cubed is just 0, so this is 1 cubed plus 2 cubed plus all the way to plus n minus 1 cubed. This sum we can evaluate. We know it's equal to this thing, where k is n minus 1. So that's going to be 1 over n to the 4th times n minus 1 quantity squared, and then n squared, all over 4. This cancels with 2 of these, and we're left with n minus 1 quantity squared over 4 n squared, or n squared minus 2n plus 1 all over 4n squared. So what happens as the limit as n goes to infinity is what happens to that fraction? Well, this is n squared minus 2n plus 1 over 4n squared. We take this limit as n goes to infinity. Well, we're going to get infinity over infinity. So by L'Hopital's rule, you take the derivative of the top 2n minus 2 divided by derivative of the bottom, 8n. And that's also going to give us infinity over infinity. So you take the derivative again. You will get 2 over 4 by L'Hopital's rule, or 2 over 8, or 1/4, which is exactly what I told you the true area was earlier. So it's appearing that this process, as tedious as it is, of evaluating the sum and taking a limit seems to work. And you can do it for Rn and you'll also get 1/4. Now, how did I get that sum that I have up there, the k thing? Well, there's a video on Canvas I would like you to watch of someone explaining this thing called summation notation. So like, for example, I equals 1 to 5 of I squared is going to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And I would like you to just go on Canvas and watch that other video. Watch the audio because the audio quality is not the best, which the creator does recognize in the comments. That's not just me being rude towards them. So why don't you go watch the video and come back? Okay, so I hope you watched the video so you understand this notation maybe a little bit more. Okay, so this notation is going to become useful for this section and the next section, which is why if you look on Canvas, I do have a check-in problem specifically on summation. So there are some rules that you could have that come with it. One of the rules is if you do I equals 1 to n of c, where c is just a number, it's a constant, there's no I in there at all, then this is just cn. Why is that true? Well, you're summing up the same number n times. So it's exactly what you would hope it would be. N times that number. Now, the next one's I equals 1 to n of I, and then you also have I squared, and then you also have I equals 1, and I'll put k here, of I cubed. Give us some of the other rules. This first one, you get n minus 1 over 2, and this other one you get n plus 1, 2n plus 1 over 6. And this one was number 4. So these are also important ones. It's a little harder to explain why this is true, so just trust me in that it is. Usually people will show these are true using proof-based mathematics, but we're not dealing with that in this class. So the fifth one I'd like to put down is that I equals 1 to n of some function of I plus a function of I. The sum does what you want it to. You can always split up this sum. Okay, and then let's clear out this function and write the last rule up here. If you have some constant times a function of I equals 1 to n, that constant pulls out. you can sort of think about it as factoring out that number. So right now it's looking pretty abstract, and I'm hoping that me going over a couple of them that I'm going to go over now, as well as you doing the check-in problems, will help. Okay, so when you're doing these check-in problems and sums in general, I do want you to do sort of step by step. You do not have to say which one you're doing. You do not have to memorize them. And I will not make you memorize them for the exam. But it should still be a logical step by step thing. Okay. So let's do a couple examples. I'm going to start with k as my index. K equals 1 to 10 of 5i. Remember rule number 6 said that 5 we can pull out of this sum. K equals 1 to 10 of I. So if you do want to write justification, that's by 6. And then this sum we can evaluate by number 2. That's going to be, our n is 10, so it's 10 minus 1 over 2 by rule 2 equals 5, and then times 5 times 9, or 225. So that's a lot easier and quicker than, say, adding out 5 plus 10 plus 15 all the way up to 50. Okay, so let's do another example. Well, we'll not make this 10 again. Let's do I equals 1 to 9, I plus I squared plus 2. By using rule number 5 twice, we can split this up into just each term, which it's a sum, so that's what you would hope you'd be able to do when you're summing things. So by 5. And each of these is their separate one. So the first one's going to be 9, then 9 minus 1 over 2. Plus, second one will be 9 plus 1 times 2n plus 1. So 2 times 9 is 18, plus 1 is 19, all over 6, plus 2 times 9. And that's by a whole bunch of rules. So by rule 2, rule 3, and rule 1. And you can compute this out. And what do you get? You get 339. One more example I'd like to do with this one then. Last example. Is, let's suppose we have this sum. I equals 2 to 9 of I squared. Well, look, my index is not the same as it was before, and that looks like a problem. I'm starting at 2. So can I really use that rule? And the answer is no, but I can do something clever. This is the same as I equals 1 from I equals 1 to 9 of I squared, but then you're subtracting off that first term. And now this thing I can do as what the rule has. So that's 9 times 9 plus 1 times 2 times 9 plus 1 all over 6. And then you just have to subtract that 1 still. So 9 times 10 times 19 divided by 6 minus 1 gives me 1139. Okay, so that's what I have for today. Be sure to get really comfortable with the summation notation because it's not going away. It's a very convenient way to start to write these problems so that you're not taking up an entire line each time. So I will see you all virtually tomorrow.